say thank the Weiss Institute for this award and for their continued support to core mathematical research. We are certainly very pleased for being awarded this prize this year. I'll talk about part of our work. Jeremy will talk about, I guess, the second part about the enterprise conjecture, and I'll talk about the first part, which is more about surface subgroup theorem and its application in low-dimensional topology, mainly in classification of three manifolds. So I have prepared the slides, which I will follow, but I will also use the Blackboard. Please, if you have questions, ask them. I'll be happy to try to answer them. So I guess I'll tell you what the surface subgroup theorem is. I will tell you about how it's being used and how it helped the classification of three manifolds. But probably the better name is virtual classification of three manifolds, and I'll mention two very recent results of other people important in this direction. We proved other theorems besides the surface subgroup and the enterprise. Perhaps they are not of the same importance, but I'd still like to mention one that I like particularly about counting surfaces inside of a three manifold. And so after this kind of introduction and statement of results and some discussion of this theory, I'll tell you about how we try to give some indication, a rough idea of how our construction goes, and perhaps say a little bit about the dynamic side of our construction, and maybe tell the audience about the mixing of the geodesic flow or the frame flow and hyperbolic manifolds. So, surfaces, closed surfaces, and really objects in this talk, manifolds that we consider will be closed typically. So, classification of closed surfaces, the topological classification was known for the longest time. It's probably the first theorem in topology. And it isn't a very difficult theorem by modern standards, mainly because we can draw those possible surfaces. They're easily characterized by their genus, or if we want to give some visual interpretation of it, with the number of holes they wrap up in space. So the point of this is that we can embed every closed surface in a tree space, and you can just draw them all. They all depend on the number of holes they wrap around. And this is very nice and important. This is used today when people study other manifolds, hard dimensional manifolds. They often study them by mapping surfaces into them, and particularly if they want to study homology or other things, topology, they would be interested in how to map surfaces inside manifolds. And of course, we need to know how surfaces look like, and we need to be actually able to decompose surfaces into simple pieces. So the point behind this simple classification of surfaces is that on the surface we can always draw a curve that's chronotopically non-trivial, which means that we cannot pinch it to a point, and yet the curve is simple. And what this means is that we can remove this curve from a surface and then obtain a simpler surface that has less complexity. And then we can keep doing this process until we arrive at pieces that are simple as possible. And in the case of surfaces, the simplest pieces are called, are three-hole sphere topologically, and we call them pairs of pans. And Mr. Thurston, he gave that name to these objects because they are certainly homeomorphic pans. Most of us were. But anyway, if one really wanted to prove the classification of surfaces, this is how the proof would go. So it's clear that it's important to have a codimension one submanifold embedded and essential inside of your manifold so that you can remove it and then thus reduce the complexity of the manifold that you're trying to describe. So classification of manifolds in general, well, this kind of classification, meaning that we can either tell exactly what they are, or perhaps you can describe their fundamental group. And it's not possible for manifolds of dimension 4 and higher, mainly because, for example, every group and if every finitely presented group will be a fundamental group of a closed form manifold, then that becomes impossible and meaningless task to classify r-dimensional manifolds. And tree manifolds are not like that. They are still, they turn out to be much more special than that. So, but it is not really possible quite to draw them all and make a very easy classification like in the case of surfaces. So something else has to be done, and in this talk we will try to at least explain what that is. So what kind of classification is possible. So after the Pelleman's geometrization theorem, the problem has been reduced to studying hyperbolic manifolds, and hyperbolic manifolds are those that allow the carry hyperbolic metric, which is a Riemannian metric with constant sectional curvature -1. And that pretty much brings geometers and analysts into business and dynamicists like Jeremy and myself, because hyperbolic metric allows one to study dynamics and geometry of these spaces and to be able to use find statistical properties of this dynamical system that I'll talk about in order to draw topological conclusions. Perhaps at the end, maybe I'll mention that some of the methods that are developed by us and other people might lead to a new proof of parts of the geometrization theorem, but that's still speculation, and that's not the main point of this talk. So, since we are talking about tree manifolds, let's bring up some examples. Well, one way of constructing closed tree manifolds is by starting with the surface, and then if you choose a homeomorphism of the surface, you can consider the mapping torus of this homeomorphism, and just to sketch what I mean by that, if you start with a closed surface, say of genus 2, the mapping torus is described as follows. First, you start the interval. So this is G, it's a closed surface of genus G, and you cross it with an interval, say 0, 1, something like that. And then you glue, so this is just a simple product, but now you glue the top and the bottom by a particular homeomorphism of the surface. On the slides as well. So by doing this, this is a legitimate and legal way of constructing a tree manifold, which is clearly going to be closed, so there is no boundary. I mean, if surface had boundary, then you would produce tree manifolds with boundary. So that's only better, so it gives us a way of constructing more general tree manifolds, not just closed. But the point of this is that these are exactly the tree manifolds with fiber over a circle. That is clear because here you have a point x and f of x, and when you identify these 2 points, then you basically this interval that connects them becomes a circle. So there is an actual mapping from this closed tree manifold onto the circle, and that's why I say that this manifold is fiber over a circle. So from now on, when I refer to manifold with fiber over a circle, this is what they are. Like. And it is pretty easy to realize that this tree manifold, its topology is uniquely determined by the homotopy type of this homeomorphism of the surface, where Thurston proved a remarkable theorem that this tree manifold, this mapping torus will be hyperbolic if and only if this homeomorphism of the surface is homotopic to a pseudo-Nosov map. I'm not going to get very much into what pseudo-Nosov mappings are, but most people know that, and there are various definitions, but I will just say that most homeomorphisms are indeed homotopic to pseudo-Nosov mapping. So this is a prevalent property of homeomorphism. So they dominate among all homeomorphisms of the surface itself. And so, if you want to, so in fact, Thurston conjecture this in the 80s, I believe, he made this radical conjecture that every tree manifold, a closed tree manifold, and now we'll be talking about hyperbolic manifolds, so I will reduce to them, restrict to those, that every hyperbolic tree manifold has a finite cover that exactly looks like this. that since Thurston was known as the virtual vibrating conjecture. And I'll say right now that this is the kind of classification of three manifolds that we are able to do, and this is certainly the most ambitious possible theorem that can be proved. So I'll tell you later that that now appears to be a theorem. But what is really the main, let's remember what we do in the case of surfaces, classifying surfaces. We need codimension 1 manifolds that are embedded and essential. So the equivalent of that in this case would be to find surfaces inside of three manifolds that are both embedded and essential, meaning their fundamental group injects into the fundamental group of the three manifolds. That's what we mean by essential. Another word for those is incompressible. In fact, you can require a little bit less than them being essential. You can just require that they're really embedded and incompressible. So if you take a simple loop, those will be on the surface. And if it's non-trivial on the surface, it will be non-trivial in the three manifold. That means incompressible. It turns out by the loop theorem that this is equivalent, that implies that the surface is essential. But so we will really think about essential surfaces inside of three manifolds, and our goal is to make them embedded, because then we can keep cutting and repeat this procedure more or less that being done in the case of surfaces. But the problem is, unlike in the case of surfaces, three manifolds need not have incompressible surfaces inside of them. So three manifolds that do have incompressible surfaces are called Haken, and this condition is equivalent to the three manifold having non-trivial homology. But there are many examples, and in fact this seems to be a prevalent thing that among three manifolds, that they tend to be non-Haken, so that they don't have embedded incompressible surfaces. So the next best thing you can hope for, and this is one way, and this is the direction in this theory took, is to find a finite cover of the manifold which would have an embedded or incompressible surface, an embedded essential surface. And this conjecture was made in the 60s, I believe, and it's called the virtual pattern conjecture. So the theorem is that which is the surface subgroup theorem, which is our main result in this direction, Jeremy and myself, is that whenever you have a hyperbolic closed three manifold, you can find an essential surface inside it. So this is certainly a necessary thing to do in order to find a finite cover and an incompressible surface inside of it. So a necessary thing in order to do that is to find an essential surface inside any hyperbolic three manifold. That has been known as the surface subgroup conjecture, which we have proven, and thus now it's called the surface subgroup theorem. I should say at this point that there are results in this direction, important partial results. And Mark is here. Mark can be proved a theorem, the surface subgroup theorem for a particular kind of three manifolds, those that are arithmetic, meaning that they have some extra structure. Their fundamental group can be realized as a lattice inside of PSL2C, where the matrix coefficients belong to some number. Well, it has some further properties. I won't get into that too much. But anyway, so there are other results. I already said if a manifold has non-trivial homology, then it certainly will have an incompressible surface, it's certainly an essential surface. So there are instances where this theorem was known before. So I will tell you about later what we were proving and what our methods are. But certainly, first, it's in order to talk about the corollaries of this theorem and what role this theorem plays in proving the virtual Haken and the virtual vibrating conjecture. Some of these are very recent results. But the first result that I'll mention is a corollary of our theorem, which is called, well, you can say that our theorem implies that the three manifolds are cubulated. So what that means is that you say that a three manifold is cubulated if its fundamental group acts co-compactly and properly on a cube complex. So a cube complex is much like a simplicial complex, except it's more special than that. Pieces of cubes, Euclidean cubes, and you have to glue them according to the rules of the cube. So you have to properly glue boundary components of adjacent cubes. And it is, so if you, in fact, if you have a group, you say that the group acts, and if a group acts on a cube complex in this way, then you will say because that the group is cubulated, or that it certainly provides you an extra structure if you just said that the group acts on a simplicial complex. So this is a more special situation, and the work of Bergeron and Weiss, which was started by Misha Sagier, but they were the ones who stated this corollary by using Sagier's idea from a while ago, was to show that every hyperbolic tree manifold is cubulated, meaning its fundamental group acts on this cube complex. I should say that these cubes are not, so the fundamental group of a tree manifold is known as so phi 1 of tree manifold embedded is to C to this sort of graceful representation here, and then the image group, which is now a lattice in this Lie group, PSL2C, acts in particular on the upper half tree space, as you've heard in some of the previous talks, as a portion to get a tree manifold that we are talking about. So already this group acts nicely on the upper half space, but that's not enough to prove, for example, that it acts properly on a cube complex, because you cannot recover a cube complex from the hyperbolic space, it's too big. So the cubes in question here are of very high dimension, and certainly not of dimension 3. Well, I should say that when we learned this corollary, we didn't really make much of it. We didn't know that. I remember mentioning this in talks 2 years ago, when I would give a talk about our work. I would mention this corollary, but I didn't really know that it was important. I cannot say that I believed in that as much back then. But it turned out to be important. So it turned out to be fundamental. So the groups that are acting on these cube complexes are, this theory was developed by Daniel Weiss, and he has put out, he written a numerous article with himself and his collaborators, and in particular he has this very long paper, something approaching 200 pages. It's a preprint, in which he developed this certainly powerful theory, except that he needs an extra condition on these cube complexes and the group actions. He needs this group action to be special, or the cube complex to be special. I'm not going to try to define what this is. I certainly myself am not an expert in any way in this subject, but I certainly can tell you, in the case of tree manifolds, what the specialness really means. It means that the tree manifold in question is actually Hawking. So if a tree manifold is Hawking, if it has an incompressible surface, then the cubulation that you get in this way is special, and his theory applies there. And in particular, one theorem that Danny Weiss proved is that the closed hyperbolic tree manifolds that are Hawking are have finite covers that fiber over the surface. So he proved the virtual fibering conjecture providing this.
Yeah, but I mean, right, he proved that if you have a closed hyperbolic Riemann manifold, then you have a cube complex that's virtually special.
Yes.
I mean, that's very, very hard work.
Yes, yes.
And from that it follows that it satisfies Nagel's criterion for
yes.
virtually fiber. But I mean, his main work was showing that Hawking implies virtually special.
His main work was showing that, okay, so your point is that his main work was showing that Hawking implies virtually special. Okay, fine. Yeah, Ian Nagel, yeah, I guess one comment I can make on in this direction is that one reason people, I'm not really quite a topologist, but I certainly spoke to many of them. And I think that just if you think about the virtual, why should you believe something like virtually vibrating conjecture? It wasn't clear. How would you possibly prove that this final coverage of fiber over the surface? That seemed like a daunting, difficult task. Ian Egel, number of 4 years ago, proved the criterion. There was sufficient condition for that to be the case, but that sufficient condition was really strong to require it. It wasn't something you can easily prove. But then Weiss, his contribution, main contribution perhaps, was to show that if a manifold is Haken, then some finite cover of that manifold will satisfy this difficult condition, which is called the Riefers condition. And then from Ian, it would follow that the manifold virtual fibers. But then a few months ago, or perhaps half a year ago, I'm not sure how I would qualify that, Ian showed that something truly strange and outstanding, but also unbelievable, is that even if you just have accumulation, if you have a group acting on a Q complex, then it's virtually special. So the action is virtually special. So therefore, this whole work of Danny Weiss always goes through.
So special action means what?
I'm not going to get into these definitions. What it amounts to Danny Weiss's contribution was to show that he was able to show that Haken is virtually special. It has to do, there are some four somewhat technical conditions, and to a non-expert like me, they are a bit technical, but it would have to, roughly saying, he would tell you how these cubes meet each other, and how some cross-sections of the cubes, which corresponds to the subsurface that gives you the cubulation, how this surface would meet itself, and that it really wouldn't intersect itself in the quotient. I understand it. I understand it that way. So it's technical, and it's kind of, you really would want to work just with cubulation. The specialist condition was technical, but it was shown that somehow it's the right thing to do, and it's been justified by Egel's contribution, who showed, but also relying on lots of Danny Weiss's work as well. That, whenever you have an action by a graph hyperbolic group dropping in a K0 complex, then find a sum of specialist. So it becomes so everything that works with this under this technical condition of specialness works virtually whenever you have a cubulation. That's the point. And this is why that corollary that we didn't really make much of in the beginning becomes important, because it does really follow from the surface Island theorem that three manifold groups are cubulated, and then you can use the theories of Egel and Weiss and their collaborators to conclude that both virtual Haken and virtual vibrating conjectures are true, and now they are theorems. In fact, something much stronger is true. You get a better picture of it. In fact, what really happens is that if you take a hyperbolic tree manifold, it has a finite index subgroup that embeds as a quasi-convex subgroup of a right-angled arcing group. So right-angled arcing groups are those that have a set of generators that satisfy either no relations or relations with the generators commute with each other. And so these groups are being very much studied in various fields of in geometric group theory, because they have a very nice presentation in this way. And once you get, so they are known to satisfy very, very nice properties, like that you can then transfer to the quasi-convex subgroup of those groups, so three manifold groups. So to conclude, what really happens is that surface groups are very simple algebraically. Those are one-related groups, and we know what the relation is. We can write these groups and draw them in every possible way. Three manifold groups are by no means easy, and we cannot really write them down and list them. But what we can do, we can say that they always, at least virtually, embed into so-called right-angled arcing groups, which are objects that, not easy objects to study, but certainly sufficiently well understood and allowed to prove theorems like this. And the conclusion is that there are other conclusions that I'm not listing really here that you can derive about groups of three manifolds. But perhaps these were the best known questions that people want to answer. So the conclusion is that every hyperbolic three manifold has this finite cover that fibers over the circle. So that is so-called vertical classification of three manifolds. Of course, that doesn't mean that, from a point of view of people who study quantum invariance and things like that, this wouldn't necessarily help them. So it doesn't mean that now they magically know everything about three manifolds, but this, I'd say, I find that very remarkable, and I'm sure most people do, that we are able to virtually say what they are this way. I draw virtual fibers. We think in ones, exactly. We delude ourselves in thinking we know everything about it.
Vlad, going back to what we were talking about earlier, can you explain to us a little bit how it's Q complex associated with the two manifolds?
I can just roughly say about it, yes. The Q complex, so the vertices of the, I'm going to pretend that the disk is a hyperbolic tree space, and the surfaces are now the lines. So, if you have a surface that is so let's say like this, if you have sufficiently many surfaces, which means really that you can separate any 2 points on the boundary of the tree ball by a lift to the universal cover of this essential surface. So list of essential surfaces are just disks. That is the particular corollary of them being essential. And in this case, they're also, I didn't mention that, they're also Weiss-Fuchsian, which means they're convex subgroups in terms of geometric group here. So they really are disks inside of the universal cover. You take enough of these copies, but finitely many of these left, and then with a particular orientation of them, and then these well-chosen finite set of lifts are the vertices of your cube point. And then you keep adding edges and hard-dimensional faces according to some rules having to do with how the surface translates out under the action of the group. But one thing I'm going to say, and that will give some idea of what this cube complex is that the dimension of the cube complex really depends on how many surfaces you have to take in order to start building this cube complex. And in case of our theorem, you really need to take a whole lot of the surfaces. So this cube complex will have a huge dimension to begin with. So it's not going to be something very low dimensional, and that is not the point. This is partially why I myself found this at the beginning somewhat unintuitive, because one would think that working, for example, on the universal cover in the hyperbolic space would be a better thing to do. And we certainly tried that.
What is the criterion for having enough surfaces?
So you would want to, so the criteria for having enough surfaces is that whenever you have 2 points at the boundary, there exists some surface that separates those points. Now you need to take finitely many copies of this so that some number, so that their conjugates, or some subset of their conjugates separates any 2 points on the boundary of the circle, or on the two-sphere in this case. Well, this construction, so this part is actually the one that was worked out by Sagir. He gave this criteria, which wasn't quite in his words. He said if you have in general a hyperbolic group and codimension one convex subgroups, and if you have enough of them in some sense, then the hyperbolic group acts on a cube complex, on a cat-zero cube complex, co-compact to it. And what Bergeron and Weiss did, they realized that follows from the surface. Well, that follows from the surface of the theorem because we actually not only construct one surface, we construct enough of them. That's what I'll talk about now. So, counting curves first. Well, I want to talk about counting surfaces, but I first must remind you where we are coming from. So this is the standard counting result in closed geodesics. In fact, this theory was developed for negatively curved manifolds, but in particular in the case of hyperbolic manifolds, or this theorem is in particular for the case of hyperbolic tree manifolds, you can, if you by BR you denote the number of closed geodesics of length most R in your tree manifold, you get this estimate, and this is known as the Margulis prime number theorem for closed geodesics. I give a little gimmick explanation why you can call it the prime number theorem. There are deeper reasons, of course, for that, and that's because the zeta function, you can express the counting prime function to count number of primes can be expressed through the zeta function, Riemann zeta function, and counting geodesics can be expressed through the Selberg zeta function. So there are different connections, but this is also reminiscent of the prime number theory. And so it's funny, we wanted to do something similar to this, but in one dimension higher. So curves are parameterized by their length, and this is obviously a continuous family of numbers, real numbers, positive real numbers. While surfaces are not, they're also parameterized by their volume, but this is now a discrete set of numbers, and it's really proportional to the other characteristic, their volume, if you like. So the right question is, if I give you a number g, which stands for the genus of the surface, and I look at how many homotopy classes of genus G essential surfaces inside the tree manifold there are, then I want to, first of all, it's easy to show that this is a finite number. It might be zero, that's certainly the hardest part, but this counting number actually can be estimated, and it's more or less a part of our construction. Some extension of our work was needed, but from our technology, it follows that you can estimate this number in this way. So, roughly speaking, the number of surfaces draws like G to the 2G, where G is the genus up to the bottom, the genus that you impose. This exponent 2G comes from the rank of the homology, as we learned in our proof. Rank of the homology of the genus G surface, that's the rank, or fundamental group, if you like. And there is some question about the constant. So our theorem is more reminiscent, as I sketch here, with this prime number theorem, which tells you up to some constant how the counting function grows. You conjecture that in fact this number S should behave much like a constant times C to the 2G. But we don't know exactly what this constant should be, and things are certainly more complicated than for counting surfaces, for counting geodesic, in the sense that when you count geodesic, this constant is really easy to evaluate. We just discussed yesterday, actually, it doesn't depend on the volume of the manifold. While in the case of surfaces, that is not so clear, and this constant might depend heavily on the topology of the manifold, and we just have no idea what the constant is or what it should be. But anyway, this is one thing you can draw from this is that there are certainly more than one. There is more than one surface, and yeah, there is a huge number of them. That doesn't quite explain why you can find a surface to separate any 2 points, but that will come in the next part of my talk. So that's where the geometry is going to come in, and geometry will tell us why this property is being satisfied. So after this kind of introduction, I would like to talk about our construction of what we are doing. So, how do we construct these surfaces? This is the question. This part of the talk is very much related also to what Jeremy is going to talk, so it should be also taken as a introduction to his lecture on the enterprise conjecture. In fact, I should say that we started collaborating by working on the enterprise conjecture, and then as we went along, we learned about the surface subgroup conjecture by reading Louis Bowen's paper, who was in some sense, pioneer of this approach, who had the idea of constructing these surfaces and solving the enterprise conjecture at the same time. He was the one to link the surface subgroup conjecture and the enterprise conjecture, and that should be mentioned here. His work was certainly inspirational. Anyway, so as I said at the beginning, to understand surfaces, you can keep cutting them along simple closed curves until you reduce them to the object called pairs of hands, threefold spheres, and every surface is obtained by assembling a collection of hands. So we want to now talk about hands inside of a given tree manifold. So now these objects are also three-fold sphere, but they actually live in a particular way inside of the tree manifold. So formally speaking, there has to be a mapping that maps this pair of hands inside of the tree manifold. And for reasons that I'm going to explain in a few minutes, we won't impose some other conditions on this mapping. So we want these pans to satisfy certain geometric restrictions. Meaning that, as I say here, we want the cuffs to be very long, and let's say all three of them to have length plus, well, very close to some large number r, plus minus epsilon. So this is the real length of these cuffs. We pull them tight inside of the tree manifold. Now they become geodesics. But because now we are mapping a surface inside of a tree space, there is another parameter, and that's the one that measures how close this pair of pans is to a flat desk. So this can be characterized by keeping track of the parallel transport along each of the cuff, and our requirement is that this parallel transport does almost nothing, but it's epsilon close to big D again. So these pans are almost like living in the plane. You can't quite have them living in a plane or in a geodesic plane inside the tree manifold, but they live very close to the plane. And so to find these surfaces, what we do is we are guided by certain principles. And the first principle is do not try to specify the surface in advance. So to find the surface inside of a tree manifold, I'm not going to tell you which surface I'm going to map. So I'm not going to say what is going to be the genus or the volume of that surface. That we don't do. But instead of, we follow the strategy that the building blocks for surfaces are these pairs of pans, and we think of them now living and floating inside of a tree manifold, and then we are assembling them as we go inside of the tree manifold, and hoping for two things. First of all, that when we assemble them, they will close up to give us a closed surface. And second of all, that the surface that we get is going to be nearly flat, nearly geodesic at all places. And this geometric condition is sufficient to guarantee that the surface will be algebraically essential, which means that its pi1 is embedded inside the pi1 of the tree manifold.
So is the cuff merely a geodesic?
Well, you can pull the cuff tight and make it a geodesic. Yeah, the cuff, you can think cuff is a geodesic. But the surface, there is no real surface between the cuffs. Well, you can construct various approximations. But the flatness condition means that you can find a surface that connects the cuffs that is everywhere very close to being totally flat. That's really what these conditions are guaranteeing.
I was thinking when you want to put two cuffs to get two pants together,
yes,
then the curves need to be very close.
They have to be the same. So you want the same geodesic, yes. That will be the condition. So you want to assemble this, you want to do it, your condition is that these cuffs coming from different pairs of pens agree, that must be the right condition. Well, here I sketch kind of a formal part of the construction which somewhat explains, addresses this question that you raised. So how do you actually glue the pens? What does that really mean? So you consider all good pens, and I should say right now that we don't know that this set is non-empty. But we will pretend that it is non-empty, that there are some good pens to talk about. But if you don't want to think about good pens, this part really has nothing to do with geometry. You can just think about any pairs of pens inside of a tree manifold or any other space, and you can try to glue them. And so this is what you basically need to do. In order to glue these pens, obvious boundary map will tell you that certain geodesics appear as boundary cuffs of the pens, as boundaries of the pens. And then you consider all the pens that are being bounded by that particular cuff. And this is some collection here, which can be, so you hope it's non-empty. It can be rather large. For example, maybe here just one element. But anyway, then you can just, no matter how elements it has, if you take twice, if you count each pen twice, and perhaps count if you like the different orientation, because you can obviously orient this pen by adding the normal vector, the choice of the normal vector. There is two choices for the orientation. You can, all you need to do in order to find the surface is to prescribe an evolution on the set of all the pens that are bounded by a given geodesic. Well, you need to do this for each geodesic separately, but every time as long as you prescribe evolution that's fixed point free at each cuff, you can then assemble the pens to get a closed surface. For example, let's just take an example of, imagine that our collection of pens has only one pair of pens. Now, you take two copies of it, which I'm going to draw another copy of the same pair of pens. Then these are just the copies of the same pair of pens. So the surface that you get, there is only one evolution that's fixed point free that you can prescribe in this case, which just exchanges the two copies along each of the three cuffs. And the surface that you get is a genus 2 surface. And it obviously, so if you start with actual genus 2 surface, it just kind of, the top pens collapses onto the bottom. That's what the resulting map is. So this is not very interesting from the point of view of what we want to do. Even if the pens that you start with are flat, when you double them in this way, what you get is not certainly close to being geodesic. It's actually opposite of it at the place where you glue. We introduce a huge bending angle pi, maximum possible bending. So this is what I mean by the number 4, that the closed surface may not be essential. We can construct them easily, but what is the hard part is to guarantee that the surfaces you get are locally are flat or really flat, which is what we are really after. So there are two things we have to do. Well, first of all, we need to even show that there is a single pair of pens, the good pens. And second of all, in order to glue them in the efficient way that we want, you really want to glue the pens together if they are literally living in the same plane. So locally, if you think of them as really being flat, then you want the angle between them, the bending angle between the two pens that you're assembling to be nearly 0. I want to just spend a few minutes telling you how to even construct one pair of pens. That is already I'm using now. And also sketch why the frame flow on the manifold, how that comes into play. So if you want to construct a closed geodesic inside of manifold, for example, one thing you can try to do, let's say that this is a manifold, in our case, a 3 manifold, you can start with the vector. You can shoot a geodesic from this vector, and then this geodesic travels to your closed manifold for a long time, eventually. And if eventually this geodesic comes very near and parallel to where you began that, then you should be able to stop right there and make a bypass, construct a curve that's very close to being geodesic, which after pulling tight is actually going to be very close to an actual geodesic. This is not the right choice of color. But anyway, so in order to find a closed geodesic, what you really need to know is that when you start the geodesic flow, and the geodesic flow is this diffeomorphism, is a family of diffeomorphisms of the unit tangent bundle that simply maps a vector onto its translate, and just shoot the geodesic in the direction and transport the vector. This is the vector, and then you run the geodesic flow. So you would need to know the geodesic flow has some kind of a nice statistical property that whenever you start from some back close to where you start, if you start with the function of the frame bundle and push it or pull it back by the frame flow, that this function is going to start to mix. And it's going to converge to its expected value, which is just its integral over the space. It's pairing with the constant function. So for example, the function has the mean value 0, then you expect that this function is going to mix and become close to 0. Well, it's not going to tend to 0, obviously, in any kind of a point-wise sense, but it should, in L2 big sense, should tend to 0, meaning that when you pair it with other L2 functions, it converges to 0. And the rate of this convergence is called the rate of mixing or decay of correlation. And it's a theorem that in the case of hyperbolic manifolds, this rate of mixing is exponential. This theorem is also true for geodesic flow or negatively curved manifolds. I don't quite remember whether the exponential mixing or rapid mixing, but either way, these kind of theories are well developed. Although this is hard to prove, and what I do in this last slide is I kind of sketch how the proof of this goes, at least in the case of constant curvature, in the case of hyperbolic spaces. So you can use the representation theory to derive the mixing of the frame flow. So the frame bundle of a 3 manifold, well, its universal cover is actually exactly the same as PSL2C. I'm not going to explain that in details, but that's pretty easy to conclude. In the same way as the tangent bundle of the hyperbolic 2 disks is PSL2R, tangent bundle of the frame bundle of the 3 spaces PSL2C. And you have the slightest acting on the space. You have this action PSL2C. So this portion itself is the frame bundle. But now what is characteristic for the constant curvature is that you have, and it's not true just in variable negative curvature, you don't have this device, you have this right action PSL2C on the frame bundle. And this action is not by isometries, but it is by measure preserving transformations that are the measures, the little measure on the frame bundle that is being used to define the L2 norm to begin with. So this right action, because it's by measure preserving transformation, uses an action, a unitary action on the L2 space of the frame bundle of the 2 manifold. So you have the PSL2 acting on this as well by unitary transformations. So you have this unitary action which then can be decomposed into irreducible components. So you can write this space as direct sum of countable many pieces, which are already irreducible components for this action. They're all invariant and cannot be reduced anymore. And then the Gelfand theory of other people tells you what these reducible components are. So these are some very tractable L2 spaces associated to the two-sphere. And then you can compute the decay of correlation directly. Basically, this becomes an exercise in Fourier analysis. And you can derive the mixing generally pretty easy by using this, well, rather deep theory. But anyway, so this is how I see the mixing here, and it's a very powerful and strong theorem. It certainly works in other rank 1 spaces. So there are versions of this theorem in other symmetric spaces. But in the case of variable negative curvature, it's much harder to prove this theorem. And other methods are needed because you don't have this right action. So the actual frame flow, just to give some indication, is that if you take a hyperbolic or loxodromic cyclic, well, if you take a cyclic subgroup associated to a hyperbolic element in PSL2C, then the restriction of that cyclic family in PSL2C is really giving you this the frame flow action on the frame bundle. The point is that, I guess, that beside the frame flow, this flow extends, embeds into a bigger group that acts by unitary transformation, and this is what gives you the mix. I mean, these ideas are used all over. I mean, even in the Teichler theory, you can conclude that Teichler flow is mixing because you have the PSL2R action. So Arthur would know something about that. So anyway, this is the idea. It's important. So perhaps I should stop here. I think I've spoken for an hour. Thank you.
Okay, thank you very much.
So this flows are also, this frame flow is an also?
No, frame flow is not enough. Genetic flow is enough, frame flow is not enough.
So there are some neutral directions?
There are neutral directions.
Yeah, just can be here. Yes, sir.
And so this,
Well, that's exactly why this mixing of the frame flow is a harder problem. I think the Piat has results in this direction. So they are not an also, but they are compact extension of an also flow. So he developed this theory.
Yeah, but one also is not easy.
For an also is not easier. Yes. Sure. But I guess that is known from before Piat.
No, for general also it's not known.
It's not known.
Probably it's not true.